the reason for introducing those parts of number theory is because we're going to apply them in the topic of public key cryptography. So in terms of cryptography for this course, so far we've only considered symmetric key cryptography. That is, both sides use the same key. User A encrypts their message using secret key K, sends the ciphertext to user B decrypts using the same secret key K. There's symmetry between the keys. But there's another approach. The problem with, or a problem with symmetric key cryptography is somehow we need to distribute keys. Somehow I need to get the key to the other side. And we need to do that in a secure manner. So public key cryptography is another approach, and we'll see some of the algorithms used for public key cryptography use the concepts of number theory we introduced. So what we'll do today is quickly mention the concepts of public key cryptography and then go through an example of a real algorithm. The principles first of public key crypto systems or public key cryptography. There are different algorithms that implement this. We'll go through an example of RSA, but there are others as well, but we'll use RSA as a detailed example. So from the beginning of cryptography up until about the 1960s, it was mainly about symmetric key cryptography, using permutations and substitutions. So we saw with DES, simplified DES, that it goes through some complex steps of all these rearrangements, permutations and replacements, substitutions. In the 1960s, the NSA in the US discovered, or is said to have discovered, public key cryptography. They developed this new technique, but it wasn't known about this until much later. And similarly, in 1970, the similar organisation in the UK were developed the first known technique for public key cryptography. But again, this wasn't made public, and the first public announcement of public key cryptography was by Diffie and Hellman, and maybe Merkle was the third guy involved. In the 1970s, some people developed a new approach which was now called public key cryptography. And their idea, Diffie and Hellman, and a third person called Merkle worked with them. Their idea was to, with symmetric key cryptography, the problem was key distribution. You need to get your secret key to the other person. And the normal ways for doing that was to have a third party that you had to trust that helped distribute the keys. But that relied on trusting some third party, some other person, to distribute the keys for you. They wanted to develop a technique that didn't have to rely on a third party to distribute keys. So you didn't have to trust someone else with your keys. And they also wanted to develop digital signatures. A signature, as you know, when you sign something, that acts as some evidence that this document came from you. You sign a document, and later people use that signature as proof that you agreed to that document, that it came from you. They wanted to develop a similar concept where you could sign some document, maybe a file, such that later it could be proved that you agreed to that document or file, that it came from you. So that was their motivation, and Diffie and Hellman developed a technique, and we'll see their technique later, but shortly later there were some other algorithms developed, and one was called RSA, which we'll cover today, developed by Revest, Shamir, and Edelman, with RSA in the name of the algorithm. But before we talk about algorithms, we'll talk about the general techniques of public key systems. Symmetric key algorithms, same key for encrypt and decrypt. Asymmetric algorithms, so public key cryptography, the other name is asymmetric cryptography because we don't have the same key for encrypt and decrypt. We have two different keys. We use one for encryption and a different key for decryption. But the two keys are related in some way. In symmetric key cryptography, how do you choose your keys? You've all did the homework. I think it was due today, correct? Yeah, okay, so you've done your homework. How did you choose your keys? Random. Okay, so you generate a random number to act as your key. In public key cryptography, the keys are not chosen randomly. There will be two keys. We'll use some algorithm to generate the keys, not a random algorithm, and they'll be generated in such the way that the two keys are somehow related, mathematically related. And what we'll require is that one of those keys will normally be made public. We can tell everyone that key. The other key is kept secret. We don't tell it everyone. So we have two keys now. So we can talk about a key pair. One of those keys we can tell everyone what the value is. So it's not a secret key, but the other key in the pair must be secret. And we give them names, a public key and a private key. So we'll see that each user has a pair of keys now. One's called the public key, one's called the private key. And the algorithms for public key cryptography will be such that if you encrypt with one key, then the ciphertext that you get can only be successfully decrypted if you use the other key in the key pair. That's what the algorithms must be designed to support. If I encrypt with a public key, some plain text, and get some ciphertext, the algorithms should be, and the keys should be generated in such a way that the ciphertext can only be decrypted using the corresponding private key. And what we'll require is that because we have two keys, one will be used for encrypt, one for decrypt, one will be public, one will be private, it must be such that it's hard for the attacker, given one of the keys, to find the other. That is, given the public key, it must be practically impossible for the attacker to find the private key, because if they can find the private key, it's no longer private, and our security is defeated. So we'll say that the algorithms require the keys to be related in some way, but even though the attacker knows that relationship, given one of the keys, it should be hard for the attacker to find the other key. And that's where our number theory will come in. Some algorithms support the feature that you use one key to encrypt, you can only decrypt with the other key, and you can use the keys in the opposite order. If you encrypt with a public key, you can only decrypt with a private key, or if you encrypt with a private key, you can only decrypt with a public key. So we'll see the advantage of that optional feature. Not all the algorithms support that. So let's introduce the terminology. We talk now about a key pair, a public-private key pair. And we think each user in our system has a key pair, their own key pair. And the keys are called a public and private key. So we'll denote the public key of user A as PUA and the private key of user A as PRA, subscript A for the user. And you think every user has their own key pair. The public key, as the name suggests, can be made public. You can tell everyone in the world what your public key is. It's not secret. And the private key should be kept secret. If you tell someone your private key, the system fails. It will not be secure. And we can achieve two different security services with public key cryptography. We can try to do confidentiality, or listed on the slide, secrecy. I want to send a message to someone such that no one else can see the contents of that message. That's what we use symmetric key encryption for. Keep a message secret or private. To do so with public key cryptography, we will use the public key for encryption and use the corresponding private key for decryption. But in practice, public key cryptography is mainly used for another purpose, authentication, proving that a message came from a particular person. And that uses the keys in the opposite order. It encrypts with a private key. Can anyone see the mistake on the slide? Down here. the last line of the slide, instead of saying decryption, should say encryption here. So fix that on your handouts. The private key for authentication is used in encryption, not decryption. I make mistakes just to make sure you're awake in this lectures, okay? So the private key is used for encryption, for authentication, and the public key is used for decryption. The TV's on? Okay. So we'll see examples of both. We'll just talk about the general concepts in the next two slides, and then we'll go through a specific example that uses some of our number theory. Let's say I want to send a message to someone such that no one else can see the message. It's confidential. So user A is on the left here, user B is on the right. Assume everyone has their own key pair. So everyone has generated their own public and private key. And we know everyone else's public key. If I'm user A, I know my own public key, I know my own private key, and I know everyone else's public key. So in this slide, user A knows the public key of user B. And user A is going to send a message to B with the aim an attacker cannot find the message. They cannot read the message. We keep it confidential. The approach is we take our message and the plain text, and we denote the plain text as M. We don't use the letter P because we use P for the keys. So we usually refer to the plain text message as M. And we use the public key of the destination. I want to send a message to B, so I use B's public key to encrypt that message. So I use some encryption algorithm, and I obtain some ciphertext. The ciphertext C is obtained by encrypting the message M using the key PUB. So encrypt a message with a key, and that key is the destination's public key. I send the ciphertext. B gets it. To get the original message back, B applies a decryption algorithm, and they use the corresponding key in the key pair, which is the private key of B. B knows its own private key, so B uses their own private key in the decryption step. Decrypt the ciphertext using B's private key, and the algorithms, the encrypt and decrypt, must be such that we get the original message back. And we'll look at an algorithm that does that. That is, decrypt using this different key, different but related key than used for encryption, and the result, the output of the algorithm, should return the original M, the original message. So for this to work, we need some algorithms such that when we encrypt with one key and then decrypt with a different key, we'll get the original input back. And for security purposes, it must be hard for the attacker to find the message. Find M. You're the attacker. You intercept the ciphertext. What do you try to do? How can you try and find the message? If you're the attacker and you can intercept the ciphertext, how do you find the message? What do you need to do? Think about, as the attacker, what do they know? The attacker knows the ciphertext. What else do they know? On the picture, the notation, what do they know? So we need to be careful now. We can't say the key because now we have two different types of keys. They know the public key. So the attacker knows, in this case C, the ciphertext is known. They know the public key of B because the public key of B is public to everyone, including the attacker. They know E, that is, they know the algorithm for encryption. They know the algorithm for decryption. What do they want to know? M or the private key? I want to know M. If I know the private key of B, then I can decrypt. Because I know C, I know D. If I know the other input, then it's easy to decrypt. So the private key, of course, must be kept private. So what the attacker's challenge is, given the ciphertext, given the public key, find M and or find the private key. And the challenge for making this secure is that the private key and the public key are related in some way. They're not just randomly chosen, so there is some mathematical function that relates them that we'll see shortly. So assuming that the attacker cannot find the private key, then this provides confidentiality because the only person with PRB is user B. Therefore, the only person who can decrypt the ciphertext is B. No one else can decrypt, so no one else can see the message. So if the attacker cannot find the private key of B, then this provides confidentiality. There's a variation, or we can use a similar technique for authentication, but what we're going to do today is go to an example of an algorithm for E and D, and then later we'll come back maybe next week and look at the authentication approach. But since you're all fresh and fresh with respect to number theory, you've all done the quiz, so we'll go through an example of an algorithm that uses the number theory that we've studied over the last few lectures. The algorithm is called RSA. And we'll go through an example. The algorithm is described on this slide, but we'll go through an example to illustrate it and explain it. There are three operations in the algorithm. There's key generation. So we need to generate a public and private key pair. Each user generates their own key pair. So there's an algorithm for doing that. You don't just choose random keys. There's an algorithm for encryption, and there's an algorithm for decryption. So we'll go through the first one of generating keys first. And to do the example, we're going to use some small numbers. But later we'll talk about, well, in practice, you will not use such small numbers. You'll use much larger numbers, but the same algorithm is used. Small numbers just so we can calculate in our head. So the algorithm is called RSA. And the first thing we're going to do is the key generation steps. We want to generate our own key pair. And the first step is to choose two prime numbers. And we'll denote those prime numbers as P and Q. Prime P and prime Q. Can someone choose a prime number for me? 2, 17, keep going. Any others? 111, I don't know if that's prime, maybe. Too hard. Some that I can calculate in my head. 71. So we choose two prime numbers, okay? And you can choose any two. They should be different. For now, we can choose any two. We will choose two small ones so that we can be sure that they're prime and that we can use them in the calculations easier. Someone said 17, and another small one, and it will help to be small just for the calculations, 11. Two prime numbers. In practice, for security, you would actually choose two very big prime numbers. Very big in terms of hundreds of digits. So that's the first step. We choose two prime numbers. Don't tell anyone the prime numbers. Okay, so they are two secret values. This is what you do to generate your key. We multiply them together. these steps are described on the slide. We'll just go through the example. Multiply them together. What do we get? Someone has a calculator. 187. So we have a new variable, n. We'll use that shortly. The other thing we need is the totient of n. How do we calculate the totient of n? Yeah, we can do it the long way. Look at all the numbers up until 187, check if they're relatively prime with 187. Or we can do it the fast way by recognizing, in this case, the totient of n is the totient of two primes multiplied together, and they meet that condition that they are relatively prime, so it becomes the totient of p times the totient of q. The totient of a number which is made up of multiplying two numbers which are relatively prime with each other is the totient of those numbers multiplied together, and the totient of a prime number is just that prime number minus 1. The totient of a prime p is p minus 1. That is the number of numbers relatively prime with a prime number is all of those numbers up until and less than that prime. So this is something we saw in the number theory examples, which is what? 16 times 10. So that's easy to calculate. And the reason we choose two primes at the start, p and q, one of the reasons is that we can easily calculate the totient, because we'll need that in the shortly. So if I chose some n which was not made up of multiplying two primes together, calculating the totient, we said calculating the totient of a large number is quite hard unless we know that that number is made up of two primes multiplied together. So this is easy to calculate. Next step, let's introduce a new variable. E. We'll choose some variable e, and the conditions of e is that it's relatively prime with 160, our totient of n. Or relatively prime, remember, the greatest common divisor of e and the totient of n should be 1. So this step is choose some e such that it is relatively prime with the totient of n. What numbers are relatively prime with 160? There are many. The other condition, I'll note here, e should be greater than 1, maybe that's obvious, and less than the totient of n. So we get to choose an e here. What about, let's try, what about 2? Is 2 relatively prime with 160? Greatest common divisor of them is not 1, so no, we can't use 2. 3? Is 3 relatively prime with 160? I see yeses and nos. Check. Three is a prime number. Can 160 be divided by that prime number? No, so that means that the greatest common divisor is 1. So yes, this one's okay. This could be the value of e, But there are other values we could choose from. We will not go through many, but what about 4? No, because in fact 2 is being ruled out, so even numbers won't work. 5? 160 is divisible by 5, so that's no good. 6 won't work because that's an even number. 7? Can 160 be divided by 7? Can 160 be divided by 7? So is it relatively prime with 160? Yes, okay, so 7 is okay. So we could have E is 7. We'll say how do we select later. 8, no. 9, you can check, is not, has a greatest common divisor of 1 with 160, so 9 is okay. And we can keep going, we'll find other numbers. 11's okay, and there are others. We just need one value. Later we may talk about what would be the better value, but let's just choose one for now. And I would choose, let's say, 7. My favourite number, E equals 7. So choose a value which is relatively prime with a totient of n. We'll go through the steps and then we'll see why we do these steps by doing some analysis. Now, choose another number, or find another number, D, such that E, we'll write it E and D are relatively prime in mod the totient of n. I'll write that a bit different. Choose a D such that E times D mod the totient of n equals 1. So we know E, we know the totient of n, 160. Find a D such that when we multiply by E and mod by 160, we get 1. So in modular arithmetic, E and D are relatively prime in the totient of n. So we can write that with our values. E was 7. 7 times something mod 160 equals 1. What is that something? That'll be our D. The easy way to manually solve that is, okay, 7 times something should equal either 161, because when we take 161 and mod by 160, the remainder will be 1. Or if we can't find such an integer, 7 times something equals 321. Why? 321 mod 160 is 1. The remainder is 1. So we need to find an integer that matches one of these conditions. We'll try some. Or, for example, 481. That is, try. Is there an integer that, or can we divide 161 by 7 and get an integer? Yes or no? Check, find the answer. So the general approach, if you're doing it by hand, is to check what numbers can we multiply by 7 to get some number which is when we divide by 160, has a remainder of 1. So 7 times something equals 161, or 7 times something equals 321, or equals 481, or keep going. In this one, it's easy. You only need to try one, I think. What do you get? 23. 7 times 23 is 161. So we didn't need to do the next 2 steps. We just need to find a value. It turns out that 7 times 23 is 161, so we'll set our D equal to 23. If we didn't find an integer here with different values, then we'd try for other values. Now we're finished. We've finished the key generation steps, and we denote the keys. We say the public key will be the value of E, and we also include the value of N in the public key. What was N? 187. And the private key, PR, we say is the value of D, 23. But for completeness, we actually include the value of N in the private key. We'll say something about that. So usually we say that the public key is the value, the pair E and N, those numbers that we found, and the private key is D and N, those numbers that we found. The same N. Before we use these keys, let's just go back and note what's secret. What values in this step should we not tell anyone? P and Q should be kept secret. Our 2 primes that we started with. N is not kept secret. N is actually part of the public key.
Yeah, but I might guess.
Right. An attack may try and find P and Q from N. Okay, so I just said P and Q must be secret, but N can be public. So if you know N, 187, how do you find P and Q? So if I gave you 187, what would you do? You'd try and find P and Q by finding the 2 prime factors. But we said in number theory that's a difficult problem when N is large. If you have a very large number, to find the 2 prime factors, P and Q, is practically impossible if those numbers are large enough. So with 187, yes, we can. I give you 187, you'll find P and Q is 17 and 11. But if I give you an N which is 4,000 bits long, then give you the task, go and find my P and Q, you won't be able to do it. Because it would take, and we'll give numbers, it would take millions of years or millions of centuries to do so. So when we move to the secure version, we'll use larger numbers. So N is public. That is known by others. P and Q must be kept secret. What else must be kept secret? The totient of N. We should not tell anyone 160. We'll see why. E is public. We'll set that as our public value. And D is private or secret. the algorithm is public. The attacker knows how I did this. And the result of the algorithm is two what we say keys, but they are actually made up of a pair of values. The public key is a value of E and N. E is 7, N is 187. I can tell everyone those. I tell you my value of E is 7, my value of N is 187. You'll need them to encrypt and decrypt. But my private key I keep private, but be careful there. The real secret value is D. I don't tell anyone D, but we often say that the private key includes also N. But N is public. Okay? You know it, it's in the public key. But in practice, when we store the keys, we usually store E and N in the public key, D and N in the private key. But be careful, the only thing secret is D. N is not secret because it's in the public key. So we have generated our keys. Everyone does that in their own way. They choose their own P and Q and generate their public and private values, and then distribute those values to others. Let's encrypt. And let's maybe I'll give you another example. Before we encrypt, make sure everyone's up with this. Let's give you another case. Generate your key. Go through the key generation again. For a different user. And to get you started, let's say that user chooses these values. P of 13 and Q 23. Generate the keys. So you generate the keys for this user. So each user does it separately. Complete the steps for the key generation. And if you can't remember from the ones I did, they on the slide, on this slide, these three steps. Choose primes P and Q, well we just did that. Calculate N. Calculate the totient of N, we'll need that. Select an E where the greatest common divisor of the totient of N and E is 1, and then find D, where D and E are the inverses of each other, the multiplicative inverses in the totient of N. That is, E times D mod the totient of N equals 1. So do those steps for a given P and Q, 13 and 23. Everyone have their own key pair? So let's go through the steps. There are different answers that you may come up with. We'll see what others come up with. So what's N? N, multiply the two values together, is what? 299. The totient of N is P minus 1 times Q minus 1, or 12 times 22, which is 264. So they were the first two steps. So just multiply our 2 primes together, gives us n. Multiply the 2 primes minus 1 together, gives us the totient of n. So they're easy to do. Choose an e such that, again, the greatest common divisor of e and 264 equals 1. And the other one that I won't write down is that e should be less than the totient of n. What values of e did you get? 5? 7? Anyone go any further? All right, so you can get multiple values, so you can choose one. Let's choose 5. We know that, what is it, 5, right, e is 5 because the greatest common divisor of 5 and 264 is 1, so e. And then if e is 5, some people did e is 7. So we'll just write that for those people. Another option, e was 7. If e was 5, what's d? If e is 5, what's d? Everyone found d? 53. Why 53? 53 and 5 are relatively prime in the totient of n. That is 5 times 53 mod 264 gives us 1. D equals 53 in that case. Why? Five times 53 mod totient of n, 264, equals 1. That was our condition. That we say E and D are the multiplicative inverse of each other in the totient of n. Remember multiplicative inverse? When we times two numbers together, we get 1 when we mod by the modulus. In this case, the multiplicative inverse in the totient of n. That is, times E and D together, we get 1. If you chose E as 7, what D value did you get? Someone chose E of 7. What D value did you get? Anyone? 151. Seven times 151 mod 264 gives us 1. Takes a few more steps to find that one. Okay, but still you can find the answer. So we have our keys. Let's use the first one. I'll call this user B. The public key of B, our second user, E is 5, N 299, and the private key D is 53, and we'll also include N here. So that's our key pair for this user, user B, our second user. a common exam question. Here are two primes. Generate your own key pair. So do those steps. We'll go back to our first user because we also did it for the first user. Actually, we can write it here. We fit it on. Our first user, let's to be clear, this was user A, the public key of user A and the private key of user A. So we have two keys. Each user has their own key pair, so two key pairs. Let's use them. We'll write them again. We've got user A and user B. What was D? 53. So each user at the start generates their own key pair. A and B have their key pair, those values. And now they exchange public keys. Let's tell each other their public keys. So what is known by each user is your own key pair plus the other's public keys. So let's say that A also knows PUB is the value stated here. Keep track of what's known. They didn't generate that, but B told them, this is my public key. And similar, A told B its public key. Exchange the public keys. So we've generated keys, exchanged public keys, and now we can encrypt and decrypt. That was our goal. For example, let's send a message from A to B confidentially. From A to B. And let's choose a message, and for RSA, our algorithm we're using, the messages must be converted to a number, and the number must be less than n. So how do we convert a message to a number? Let's say I want to send the message hello, then we need some way to convert that into a number. So we can convert it to binary, maybe using ASCII encoding, and then treat that sequence of bits as some integer. Okay, so the message is a number in this case. So I will not start with a message. I'll just choose a number that we say is our confidential message. Anyone want to send a message? What message would you like? Hello, but we'd like to make my life easier. Let's just choose a number. Okay. So if it was hello, I would convert that using ASCII to a sequence of 5 times 8 bits, 40 bits. And then we could treat that as an integer, a 40-bit integer. But in fact, with RSA, the number that we get, that we send, must be less than n. Okay, so here our n's are what, 299 or 187. We need a smaller number in this example. With a real example, we would have much larger n, and we could encrypt hello. So for this example, I'll just choose a number, maybe small number. We've used 7 many times here. Let's choose a different number. Let's try our random number generator. Choose a number between 10 and 20.
15.
15, good. That's our message. Now, again, in practice, our message needs to be converted into an integer. There are some conditions. But let's say we want to send the message from A to B, and that message M is 15. So, our encryption algorithm now. To encrypt plaintext M, where M is less than N, first, what value of N? Whose key am I going to use to encrypt this message? A is going to encrypt M and send the ciphertext to B. Whose key is A going to use? Which key? A knows 3 keys, PUA, PRA, PUB. Which one will I use to encrypt this message for confidentiality and send it to B? I use the destination's public key. Okay, so I'll use PUB in this case. Maybe we'll denote it as we'll encrypt. To get the ciphertext, we'll encrypt using PUB M. To send a message confidentially to someone else, use their public key. And the algorithm, M must be less than N. Is M less than N? N in this case is 299. So yes, we've met that condition. M is 15. To encrypt, take M, raise it to the power of E mod by N. In our case, M is 15. E in the public key of B is 5. Mod by 299. What do we get? We need a calculator. 15 to the power of 5 mod 299. 15 to the power of 5 mod 299. 214. Okay, the answer, the ciphertext is 214. We send that to B. That's the ciphertext. When B receives the ciphertext, they decrypt. Which key do they use to decrypt? It was encrypted using the public key of B. Public key ciphers work such that if you encrypt with one key in the key pair, you can only successfully decrypt with the other key in that same key pair. This was encrypted with the public key of B. We must decrypt with the private key of B. So the M that we get when we decrypt will decrypt with the private key of B, the ciphertext received, and we'll see what we get. And what is the decryption algorithm? It's in fact the same as the encryption algorithm, but we use some different values. Decrypt is take the ciphertext, raise it to the power of d, that private value, mod by the same n. Let's try it and see what we get. C to the power of d mod by n. What is n? N is 299. So again, we're using the private key of B. D is 53. N is 299. So we use those values. And C is our ciphertext. 214 to the power of D. Hope our calculator will handle this. Mod N. (214 to the power of 53 mod 299). What do we get? 15. That's good. If we didn't get 15, we'd have a problem. Our requirements of encryption and decryption is when we decrypt with the right key, we'll get the original plaintext back. If we didn't, the algorithm is of no use to us. And we can prove later that we will always get the same message M back. So that's it. That's RSA in use. We encrypted some message M using the public key of B, send the ciphertext to B, B decrypts using their own private key. And the algorithm is designed such that you'll always get the same M back if you follow those steps, as long as nothing's changed. If you follow these two steps, we'll get the original M, 15. A common exam question is prove why. Prove why M will be the same. We'll see that, not today, we'll see that next week. Any questions before we look at some potential attacks?
So the encryption and decryption algorithm themselves are not very complicated, but
right. And the beauty of RSA is that these encryption and decryption algorithms are very simple. Take some number, raise it to the power, mod by n. The encryption and decryption algorithm is in fact the same. So implementation-wise, they are the same. It's just that the numbers that we use are different. Something to the power of something mod n. Something to the power of something mod n. Very, very simple to describe, but turns out to be very secure if we use appropriate values. And appropriate values usually means large numbers of P and Q to get started, large primes. Whereas if you remember DES, we went through all those, or simplified DES even, we went through 2 rounds where we have permutations, S boxes, key generation, XORs and so on. Whereas here encryption is just M to the power of E mod n. Very simple, but very secure. Any questions of how to generate keys or encrypt? Okay. Let's then look at why does it work and why is it secure? Let's look at what the attacker may do to try and find M. What does the attacker know? In our specific example, what values do they know? They know the public key of B. They know the algorithms. Okay, they know the exact steps which we use for key generation and encrypt and decrypt. That's public. And they know the ciphertext. So they know the algorithms, the ciphertext, and the public key. So we know C equals 214. We know, what else do we know? We know the public key of B. E was what? 5? Is that right? N was 299. And we know the algorithms, the steps which we use. What do we want to know? Let's say we want to find the message. The idea was confidentiality. We want to find M. How do we find M? Let's look at the algorithms. Let's write them down, at least the encryption and decryption. Encrypt we know was C equals M to the power of E mod N. So let's write that with what we know. C is 214. M we don't know. E is 5, we know that. N we know is 299. So the attacker knows this, easy. They want to find M. We have an equation here. 4 variables, C, M, E, and N. 3 of them are known. Normally with an equation with 4 variables, 3 known, we just rearrange and find the unknown. How do we do that? What operation do we do to find M? Or what's it related to? How do we find M? By solving this equation. What could we do? Well, what operation is this like? Or a brute force attack could be to try all values of M. Let's try M equal to 1. Does 1 to the power of 5 mod 209 equal 214? No, M is not 1. M equal to 2. 2 to the power of 5 mod 299. We don't get 14. Keep trying. Eventually you'll get an M that when you raise to the power of 5, mod by 299, you'll get 214 and you've found M. So a brute force attack here, try all values of M. Go away. Try all M. That will work. How do we stop that? How do we stop a brute force attack? Make M large. Or allow M to be large. Because a brute force attack requires the attacker to try all possible values of M, or at least half, or all in this case. So if M can be a very large number, then they have to try many potential values. And in fact, to make M large, in the algorithm, the condition was M should be less than N. So N must be large. For M to be large, N must be large, because M must be less than N. So we need to choose an N which is very big. That's one security condition. But instead of the brute force, try all M. Can't we solve this? Can't we just rearrange it? What do we rearrange? What do we get? It's something about the logarithm. Remember, the discrete log of some base M in mod 299 of 214 equals the index 5. So it's related to solving a discrete logarithm. In fact, it's not finding what the index is, it's finding the base that gives us that index. And it turns out it's essentially the same difficulty in terms of problems. Finding the base or finding the index are hard problems to solve if you have large values. Solving discrete logarithms is considered computationally infeasible if we have large enough values. So step 1 for the attacker, try all m. Step 2, have some algorithm to solve a discrete log, and that's not possible, again, if n and m are large. So finding m directly from that equation, if we have the appropriate size values, is impossible in RSA. What else can we do as the attacker? Maybe another approach. All right, if we can't find m, what's the other equation? The decrypt equation, we know that. We know that m equals c to the power of d mod n. We don't know m. We know c. We don't know d. We know n. So we have an equation, we've got two unknowns, so we need to find one of those unknowns. Well, we couldn't find m. Can we find d? If we do find d, solving this is easy. Just use my calculator. So if we can find d, we will find m. How do we find d? Well, we know something about E and D. E times D mod the totient of n equals 1. We know E, so this is the equation from our key generation algorithm. We know E. We don't know D. Do we know the totient of n? Do we? How do we know it? You're the attacker. You don't know anything we did before. Find me the totient of 299. What do you need to do? Factor it into its primes is the easiest way to solve that. You could do the manual approach, go up to 298, but that would take too long if it was a large enough number. So to find D, we need to find the totient of n. All right. And there are two ways. Factor into P and Q, and then it's easy. Or the other approach, the brute force, that is, try all the values up to n minus 1. All right, the manual approach. With large enough values of n, it's computationally infeasible to try all the values from 1 up to n minus 1 and count the number of numbers relatively prime. So with large n, it's practically impossible to manually solve the totient of n, and factoring numbers into their integers is practically impossible as well. We'll stop there. Think about that. Go back to the number theory notes just to make sure you know these steps that we're using. And remember, factoring a large number into its primes is hard. Calculating the totient of n without doing that is hard. And solving discrete logarithms is hard. And that leads to the security of RSA.